This was my regression equation of y on x. Okay, I'm again writing it over here. Regression equation of y on x. And this quantity that I have marked blue, this quantity is actually called the regression coefficient, which we denote by byx. This is the regression coefficient of x on y. So byx is actually called the regression coefficient of y on x. Similarly, if I talk about the regression equation of x on y, then you know the regression equation is x minus x bar rxy into sigma x by sigma y into y minus y bar. This coefficient that I have marking over here, this coefficient is actually called bxy into y minus y bar. So here bxy is equal to regression coefficient of x on y. Now you see that if I, what is the formula for, therefore, what is the formula for the regression coefficient for of y on x? It is the, this is the formula. And what is the formula for regression coefficient for x on y? This is the formula. Now you see, carefully observe one thing, one beautiful thing, that if I take the product of these two regression coefficient, if I take the product of these two regression coefficient, what I get is the following. I get rxy into sigma y by sigma x multiplied by rxy into sigma x by sigma y. and this sigma y and that sigma y will cancel. This sigma x and this sigma x will cancel. So we will get a beautiful result, which is rxy whole square is actually the product of the two regression coefficients. So correlation coefficient squared gives you the product of two regression coefficient. It's a very important formula, and it often helps us to solve problems. Okay. Now, some important results can also be derived from this particular case. From regression coefficient also satisfy some other important properties that I'm going to describe right now. One of the important properties of the regression coefficient is the following. So what I have got here, an important property which says that if I take the correlation coefficient square of the correlation coefficient, then we will actually get the product of the two regression coefficients. And you know that in this particular case, in this equation, if I name this equation as 1 and this equation as 2, these are actually the straight line equations. And in straight line equations, these regression coefficients, they are actually denoting the slopes of the straight line. Here also it is a slope of the straight line. This is another important observation in this particular case. Now, the important property that we can they satisfy among one another is the following. One another important property is that if one of the regression coefficients is greater than unity, the other must be less than unity. The other must be less than unity. So suppose we are in a particular problem, you have got two regression coefficients. It is saying that suppose one regression coefficient is byx. Let one regression coefficient is byx, which is greater than 1. Okay. Now, if byx is greater than 1, immediately we can say that if I take the reciprocal of this should be less than 1. We know that correlation coefficient Rxy is actually lying between -1 and +1. I talked about it in the last class. This is the limit for the correlation coefficient, which implies that the square of the correlation coefficient will be definitely less than or equal to 1. This is a kind of property of the real numbers. Okay. And from this, we can easily say that the product of the two regression coefficients is less than or equal to 1. Give it equation number 1. Because just now we have proved that the correlation coefficient square is the product of the two regression coefficients. So from 1, we say that we find that bxy is less than or equal to 1 by byx. And if I give it equation number 2, we can say from equation 2 also that 1 by byx is less than 1. So what have we found? We have found that byx is greater than 1 if one regression coefficient is greater than 1, then another regression coefficient is less than 1. We have proved it. The result is proved. This is one very important property that the regression coefficients satisfy among themselves. Can I go to the next page?
Yes, sir.
Okay, so the next property that the regression coefficients satisfy is the following. It is saying that the arithmetic mean of the regression coefficients, arithmetic mean of the regression coefficients is greater than the correlation coefficient. Correlation coefficient R provided R is positive. Now these properties that I'm actually showing you, if you are sitting for the offline examination, then these proofs actually come in the examination. But if you are thinking of the online examination, obviously the proofs will not come, but these results, on the basis of these results, simple problems, short problems, MCQ type problems can be asked. So you have to know these results very well. So the proof of this particular theorem is actually very beautiful. According to the statement of the theorem, what we need to prove is the following. We need to prove that arithmetic mean means the half of these two items, because there are only two items, so their arithmetic mean will be the sum total of these two divided by half. This should be greater than R. it should be greater than R. And if it is to be satisfied, we need to prove this. That is, if it needs to be satisfied, if it needs to be satisfied, we must have the following. We are going to substitute the formula for byx and bxy. We know that we are writing, for the sake of the problem, we are writing rxy as simple r. So this would be r into sigma y by sigma s, and this would be r into sigma x by sigma y. So if first line needs to be satisfied, then the second line needs to be satisfied. That is, if, let us do a bit of calculation over here. Take r common, and we are going to write sigma y by sigma x plus sigma x by sigma y. This must be greater than r. That is, if you can cancel r from both sides. This should be sigma y by sigma x plus sigma sigma x by sigma y. This should be greater than 2. That is, if sigma y square plus sigma x square greater than 2 sigma x sigma y. That is, if sigma y square, sigma x square plus sigma y square minus 2 sigma x sigma y greater than 0. That is, if sigma x minus sigma y whole square greater than 0. And which is pretty obvious, because it is a minus b whole square. It is always positive, which is obvious, which is a fact. And therefore, this assumption that we have made over here, this assumption is correct. And therefore, the result which we need to prove is proved. Hence proved. Hence, we can say that arithmetic mean of the two regression coefficients is greater than correlation coefficient R. And if you carefully observe, there is one condition given, which is saying that provided R is positive. Why it is saying that? Where do we apply this particular property? We have not applied this particular property. So those who are present, can anybody tell me that have I used this property anywhere in this particular proof? Or it is just like that? It is true for any R. Have I applied this particular property for anywhere?
So while cancelling that R?
Yeah, while cancelling that R, because cancelling that R doesn't have any meaning. Actually, we are dividing both sides by R. Dividing both sides by R, and we know that the divisor cannot be, the divisor must always be positive. And this can only be done when R is greater than 0. And therefore, this condition is there. So this condition has been applied over here. Now, suppose you are not careful enough and you have got two lines of regression, and you want to calculate, you want to check whether their arithmetic mean is greater than the correlation coefficient. And you may find absurd result, because probably the bivariate distribution on which you are working, probably it is giving you the negative correlation. If it is giving you the negative correlation, then this result will not hold. This result will not hold. Okay. So there are other properties also in this regarding regression coefficients. Such one of the properties like this. A third property that I can mention is that regression coefficients are actually independent of the change of origin but not of scale. But not of scale. This property is another important property. Change of origin and scale means you are going to introduce a new variable u and a new variable v in the following manner. The formula that you are going to apply over here is the variable x is getting changed to u. Here x is changing to u. And here you are writing y minus b by k. That means your original variable y is getting changed to v. The origin shifted in the first case, if I name it 1 and if I name it number 2. So in the first case, origin is shifted to the point A, and scale is changed to H. In the second case, origin is shifted to the point B and scale is changed to K. Okay, these are the formula for change of origin and scale. And if this is so, then we can write the variable x as a plus hu. We can write the variable y as b plus kv. Okay, and the constants, these constants that I'm playing with, a, b, these constants, these are constants actually. A, b can be positive, it can be negative, can be anything. But h and k, this must be greater than 0 because they are divisors. Now you have to remember one result. I have not proved it, but you can prove it. This result that I'm marking over here, you can try to prove it by yourself because I'm going to use this result over here. Results are, if we change the variables in this manner, then the quantity covariance, this is called covariance of x and y. Cov stands for covariance of x and y. This will be, according to the formula, this will be covariance of uv. So you see the covariance is actually independent of change of origin. What I'm seeing over here, this quantity is independent of change of origin, but not of scale. Why? Because the quantities h and k are present over here. Okay. Next, we need to know the change in sigma x square. That will be h square into sigma u square. Here also, and sigma x, sigma y square, this is k square into sigma v square. This result actually comes from the basic statistics. So this means variance is independent of change of origin, but not of scale. Now, if this results, if I want to apply these results over here, what we actually get is the following. We get so we want to find what we want to know about the regression coefficients. Okay, so you see that regression coefficient byx, so for example, is given by the formula rxy into sigma y by sigma x. And rxy in turn is given by the formula covariance of xy by sigma x into sigma y. This is the formula for rxy. And we have sigma y by sigma x. So it will imply covariance of xy by sigma x square. This is another form of byx. So if you are careful enough, if in the examination you are asked what is the connection between byx and covariance, you will have to tick on this. Okay. And you see that I can replace these quantities over here. Covariance of xy is hk covariance of uv. So I can put it over here, hk covariance of uv. And in place of sigma x square, I can put h square into sigma u square. So what do we get? We get we get k by h covariance of uv by sigma u square. Now carefully observe, if covariance of xy, if covariance of xy by sigma x square is equal to byx, if it is so, then it is quite obvious that covariance of uv by sigma u square, this will be same as bvu. So what we find from this, we find byx is actually equal to k by h into bvu. So what is our conclusion? Our conclusion is regression coefficient is also independent of change of origin, but not of scale. Regression coefficient is also change of origin, but not of scale. So this is another important result that is actually very important for our purpose. Okay, questions can be asked from there. And here is a little homework for you. I'm not going to do it right now because I know you are a little bit of tired. That you are going to find the angle between two lines of regression. You are going to find angle between two lines of regression, and I am also only providing you the formula. Formula is the following. You are going to find the hint. You are going to find the formula in the following manner. If the angle is theta, it would be tan inverse 1 minus r square by r sigma x into sigma y by sigma x square plus sigma y square. This is the formula. So you try to solve this particular problem and try to deduce this particular formula. And if you face any difficulties, then you ask me and I'll try to help you out in this regard. And also try to find out some special cases from here. Find out what is happening when r equal to 0. Case 2, when r is equal to 1. Case 3, when r is equal to -1. Try to find out the special cases. Depending upon the correlation coefficient's value, how the angle between the two lines of regression will change. Try to find this out. This is a homework for you. So with this, I'm going to conclude my today's session. I hope you do not have any problem. If you have any problem, I'm here. If you do not have any problem, then you can leave the classroom quietly. And once you all leave, then I will also end today's session.